Well, hello everyone, and welcome back to Prep 8. So on this tab, we're looking at a one sample Z problem for a cruise line. Bobcat Cruise Line wants to determine if the average customer satisfaction rating for their fleet differs from the industry standard. The industry average satisfaction rating is 8.5 out of 10. Which is pretty high, with a known standard deviation of 0.8. The company randomly samples 100 customers from various cruises and collects their satisfaction ratings. At a 0.05 level of significance, they want to test if their average satisfaction rating is different from the industry standard. So the key word in that paragraph is different, because as soon as you see the word different, you know that it is a two-tail test, because we don't know which direction we might be different. So on the case here, we'll pick two-tailed. The distribution, since we told you it was a Z test, the distribution is Z. That's also mentioned here on all these tabs. Down the road, you'll have to guess a little bit more because we will have Z's and T's mixed in. But for now, just Z's. The null hypothesis is no significant difference, and the alternative hypothesis is that there is a significant difference. Now, really importantly, I'm going to pick the option that says a significant difference amongst the mus, in other words, the populations, as opposed to a significant difference among the samples, all right? And that's because we're doing inferential statistics, so our conclusion is about the population, not about the sample. Okay, so what's Bobcat X bar? That is the average of all these values. What's the standard deviation? Standard deviation dot S, because it's a sample of all these values. And what's the count? It's the count of all these values. Okay, and then we know the industry from the problem, it's 8.5, and the industry standard deviation from the problem is 0.8. So here we are, and there's the industry, right? So it looks like we're higher than the industry. The question is, are we significantly higher? Or not, or is that just random sampling variation? All right, so let's get the sampling distribution of the sample mean, the mu, which is always the exact same as the population mean, so it's just going to be equal to the industry. And then the standard error, which is going to be the sigma here, divided by the square root of the sample size, which is 50. All right, now we have a lot more information to look at in this first graph. So here's our sample. Here's the population mean. And here's the sampling distribution of the sample mean, meaning that like if we took like 1 million different samples and had all these little dots, each one of those representing a sample, actually representing the sample mean. So you can imagine all these curves going through here, and then at the very peak of the curve is one of these dots. So that gives us an idea of where we stand. We seem to be way out here in the tail. So this is kind of looking like a reject, but we don't know that for sure yet. Strongly suspected, though, because we are more than two standard errors away from the mean. So let's keep going. So we take the difference of Bobcat minus the industry, and then the z-score is going to be this observed difference that we just found divided by the standard error. And that's a z-score of 2.21. So way out here. All right, now let's calculate the probability of that z-score. And for that, we're going to use this table here, which is going to help us. Now, you could challenge yourself. In fact, I'd actually recommend that you try to challenge yourself so that you sort of figure out which of these variations to use, or you can just look at the table. So in our case, we have a z-score which is positive, and it's a two-tailed test, right? So it's a two-tailed test, and our z-score is positive, so the formula is going to be 2 times 1 minus. All right, so equals 2 times 1 minus norm dot s dot dist and then the z-score, and then true, and close parentheses twice. And so our probability is 2.71. So let's get the rejection region over here. So we're going to if you think about it, we're sort of going counterclockwise. So we went down the left column, and now we're going to start sort of back up the right as far as calculating our values. So alpha is going to be 5%. And then for two-tailed, we're going to use norm dot s dot inverse of that probability, copy that across, and we run into a problem here because now we're in the right tail, so we actually have to do for these probabilities over here, the 1 minus. And then copy that across. All right, and now we have all of our rejection regions here. You can see clearly that we're in the rejection region, so this is going to be reject the null. But if we're going to reject the null hypothesis, that means that we're effectively saying, hey, our dot out here, this red dot, right, which is way over here, our dot is so far out that we're actually going to claim that this sample came from a different population. And that different population should have a different population mean. So what is it? And that's where the confidence interval comes in. So we're going to start with our sample x bar. And we're going to build the confidence interval around it. So it's going to equal to that sample x bar minus the standard error, our favorite number, times the critical value of two-tailed approach. And this is just in order to give us a 95% confidence interval, in the same way that we were sort of effectively creating a 95% rejection region here. That's why we can reuse that number. And so that gives us our lower bound of the confidence interval. And then to get our upper bound, it'll be that plus, this time, this standard error times the two-tailed right. And the only reason we pick the two-tailed right is because we want that number to be positive. Makes the math easier. All right, so here's our confidence interval. So what we're effectively saying is, look, we're not a member of the national population. We're different. And we think that our value is 8.75. And it's probably really close to that in the middle. But we're 95% confident that we're somewhere between 8.53 and 8.97. And you'll notice that when you reject the null hypothesis, the confidence interval never includes the original population mean. And if you fail to reject, then of course it would include the original population mean, because after all, we're part of the original population. Okay, so let's come down to our decision questions. So the decision is that we reject the null. In terms of a PV approach, what would it be? Probability approach, probability value approach, or p-value approach. We're going to say that we are less than alpha, right? Because alpha was 5%. So we're less than that at 2.71, which means we come from a different population. In terms of a critical value approach, we are less we are more extreme than the critical value. So here was the critical value, 1.96, and we are more extreme than that because we were at 2.21. So 2.21 is more extreme. Extreme means simply further away from zero, so we're more extreme. And you can be more extreme this way, but you can also be more extreme the other way, positively or negatively more extreme. That's why we use more extreme instead of saying greater, because otherwise it wouldn't handle the negative numbers well. Okay, so our conclusion is, well, what is our conclusion? Our conclusion is that there is a significant difference. Remember, the alternative hypothesis was there's a significant difference. So we know there's a significant difference, but we actually know at this point more than that. We know that we're significantly different, but we also know the direction that we're different. And so what's the direction that we're different? Well, we're at 8.75. The industry average is 8.5. So we are better than, more than the industry average, and we can state that conclusively now. So Bobcat mu is significantly greater than the industry average, which is good since this is satisfaction ratings. You want to be better than the industry average. But there is a caveat that we could be committing a type 1 error, which is that we're rejecting the null hypothesis when it's actually true, because that after all is possible. Okay, so now let's answer these multiple choice questions. We've dropped down menus. So what does the result of this two-tailed z-test indicate about the Bobcat rating compared to the industry average? Well, we're significantly more. We just said that. HA, meaning the alternative hypothesis, is non-directional in a two-tailed test. However, if we reject H0, the conclusion has a direction. So which is true about our current situation? So the alternative hypothesis that we originally started out with was this one, right? That they're not equal, right? Because remember, the H0 is that they are equal. So the alternative was they're not equal. In other words, they're different. But our real conclusion is that since the conclusion can be directional, our real conclusion is that our mean is bigger than the mean. Our mean means our population mean. The population we actually belong to is bigger than the population from the null hypothesis. And so if the confidence interval does not include H0, and it doesn't, right? See, there's mu H0, that black dot. The confidence interval doesn't include it. Well, can we conclude? That would mean that we reject the null hypothesis, which is what we did. The lower bound of the confidence interval is very close, right? See, look at it, it's almost touching mu 0. Which of the following would get it further away? This is a great question. What would you have to do effectively to squeeze the confidence interval closer around that sample mean? And the solution to most of these questions, when we ask you how could you make things better, is to increase the sample size. I'm going to show that, though, and this is actually kind of fun. So what you can do here is say, well, let's say I really didn't know the answer to that question. Our sample size was 50. What if I change it to 500? Right, so that's much bigger, 10 times bigger. So I'm going to hit enter and watch what happens to this when I do. Okay, notice that the confidence interval got much closer to the sample mean. This is also an interesting thing to do if we ever give you one of these questions about, what influences what, because you can change this value and then watch all the values downstream, which will suddenly become red because this one is changed. And the good news is that you can do all that and then you can just hit undo and go back after you've seen the change. All right, for a z-test, does the height of the red dot matter in the first graph? So the height of this red dot, does it matter? Well, what would the height of the red dot actually indicate? The height of the red dot is going to help indicate if it's a skinny or fat distribution, right? So the higher the red dot, skinnier it is. The lower the red dot, the fatter the distribution is. Well, what's controlling whether it's skinny or fat is the standard deviation, right? So So the question is, does the standard deviation of the sample matter? And you can actually answer that question by coming over here and changing it. Like right now it's 0.25. What if I made it like 2? And you'll notice that the graph changed, that number changed, but none of the numbers downstream changed. In other words, that number is not used in any further calculation. So if it's not used in any further calculation, I'm going to undo, then it doesn't matter. Why doesn't it matter? Why wasn't it used? It wasn't used because we had the industry standard deviation. So we didn't need the sample standard deviation. We had a standard deviation that was better than the sample standard deviation. So we went with that in the ensuing calculations. Now, when we get to t-tests later on, we won't have the industry standard deviation. In fact, you could argue that in most cases you don't have that. And so the only standard deviation that you have is the sample standard deviation, and so you use it as a replacement for the industry standard deviation in the downstream calculations. So for a z-test, does the height of the red dot matter? The answer is no. The sample standard deviation is not used to calculate the standard error. And that should give us all the points. It does, 32 out of 32. And we're done. And we'll see you in the next video.